Hello, ladies and gentlemen. Today we're going to look at section 1.3, so that's energy and equilibria. It's really important that you're reading along in your textbook and also going back to your unit study guide, defining those words and using your own words, defining the vocabulary as well as coming up with an example, and then answering the relevant questions. You really have to know the vocabulary. It has to be memorized because it's going to come up on your exam as well as throughout this entire course. So as we look, we're going to start by talking about energy. So energy is extremely important for all ecosystems. So no life on Earth could exist without an input of energy. Generally speaking, we know that our main source of energy here on Earth is the sun and solar radiation. However, there are a few specialized communities that live in these deep geothermal vents under the ocean that do not depend on sunlight as their energy source, which is also extremely interesting. But going back to the big picture, when we're looking at energy, we're generally talking about the energy from the sun, and we're trying to examine how efficiently that energy is moved throughout the ecosystem. So we're going to be looking at the flow of energy, particularly in the next unit, throughout trophic levels or feeding levels between organisms. So we get this input of solar energy. We know that producers absorb that energy and they convert the solar energy into chemical energy in the process of photosynthesis. And then it gets passed on to these other organisms or these consumers within the food chain or food web. There are a couple of laws that govern how energy is moved throughout a system. And this is the first and second law of thermodynamics, which you will have to know. So we'll start with our first law of thermodynamics. So the first law of thermodynamics is the conservation of energy, which just says that energy is neither created nor destroyed within a system. So that's something you have to have memorized. It just has to be memorized by heart. You have to be able to recite it. So in nature, we're saying that our energy comes from the sun, and it moves throughout those food chains and food webs. And that's what we're going to be looking at. So how it's transformed, how it's moved from one area to another area. So if energy cannot be created nor destroyed, that means that energy has to change. So it changes from the form in which we take it in to how it's passed on throughout the system. So in the corner we have a bear. We can see our bear is just caught a fish and is going to eat this fish, and it'll use that energy in different forms. So it'll take in the fish, it'll convert it into energy within the body that can be used in respiration. So it'll convert it into ATP, or that cellular form of energy. It will also produce a lot of heat, which is not particularly useful to the organism, but is given off as a form of less useful energy. And then we see that it's not perfectly efficient, so some of the energy will just be removed or defecated out as well. So we're looking at the systems. Two major processes have to occur. So we talked about systems and whether or not they're open or closed or isolated, and all of those definitions related to the flow of energy and the flow of matter. So all ecosystems require energy, and they require some sort of cycling of chemical elements or matter. And there were two main ways that these flows occurred. One was transfer, so that's just changing location from one area to another. And then there was transformation, which was changing form. So that meant that whatever matter we're looking at, whatever chemical we're looking at, it's either having some sort of transformation from one type of molecule to another type of molecule, or from one state to another state. So we looked at the water cycle in our practice homework and discussed how water can be transformed by changes in states. So basics for the first law of thermodynamics. So if matter cannot be created nor destroyed, it can absolutely change forms. So we get solar energy transformed into chemical energy by photosynthesis. We depend on that a lot because anytime you eat a plant or well, anytime you eat a plant, you are eating its stored chemical energy. So if you eat a potato, you're actually stealing the potato plant's stored chemical energy that it was creating for itself. We also know that other organisms or consumers can take in that chemical energy and we transform it within our bodies through the process of respiration, which also has some waste as well. And eventually, when organisms die, their bodies and energy that are stored within their bodies will be recycled as well through the process of decomposition. All right, so looking at this slide is a little bit complicated because of this diagram, but all it's saying is that yes, energy is transformed and moved around a system, and we're saying that it's going from more useful forms to less useful forms, but that doesn't mean that the energy is actually lost. Even though sometimes we use that vocabulary, it's inaccurate. What we are saying is that some of the energy goes from useful forms to less useful forms like heat, and that heat is there, okay, within that ecosystem. So it's not lost, it's just transformed into something that's not useful for us within the ecosystem. So then we're going to take a look at the second law. So the second law of thermodynamics says that energy goes from more useful forms into less useful forms. So it goes from these more concentrated forms into more dispersed forms of energy. So all we're talking about is its usefulness tends to decrease. So if we start off with something extremely valuable, like solar energy, which is very concentrated, hitting the surface of the Earth, as it moves up a food chain, a lot of the energy gets transformed into heat energy, and there's less available energy that's useful at the higher trophic levels. Right, so this is another way of looking at the information. So we're saying that the total amount of energy available within the universe is always constant, but the amount of useful energy decreases with each transformation. Now, this is actually one of the main arguments to be a vegetarian and why people think that being a vegetarian is more environmentally friendly. Because as energy is transferred from one organism to another organism to the next, okay, up the levels of a food chain, then there's less available energy. So some of it is always transformed into these less useful forms. So people believe that if we all ate just producers and we kind of lowered ourselves on that trophic level just to be primary consumers, then we'd be conserving energy that goes into food production. It's just something to think about. So entropy is the term that goes along with this second law of thermodynamics. So entropy describes disorder within a system, also described here as randomness. So the disorder or the randomness within a system is always increasing. So as we go through many, many, many energy transformations, the system gains entropy or becomes less organized because a lot of that energy gets transferred into less useful forms. And the less useful form of energy that we're talking about is heat again. So we're always talking about heat. So the amount of available energy within the trophic levels is much higher at the producer level than it is going to be at the top trophic levels, which might be like a tertiary or possibly a quaternary consumer, which tend to be carnivores. So again, this is the argument to be a vegetarian, though I am not a vegetarian. Right, so you might be thinking, where is that energy going? So if we just think about a scenario in which a lion is chasing a zebra to capture its food, right, so energy is the ability to do work. So the lion is using a lot of its energy, its stored energy from its previous meal in order to capture the zebra. However, in that whole process, it's also going to be losing or transforming a lot of that energy into heat as well, which is considered wasted energy, useless form of energy. Oh, you're going to see quite a few of these coming up very soon here, but this is an energy pyramid. Okay, so a trophic level pyramid. So just showing different organisms within a food chain and the amount of available energy within that trophic level. So we can see they're always pyramid shaped because we have more available energy at the bottom, so at that producer level, in this case phytoplankton, than we do at the top. So the top of this one is a tuna. And I know that we often think of tuna as these itty bitty little fish because we always see them in a can, but tuna are huge organisms. So a tuna could be twice my mass. It is a very, very, very large organism. So here you can see it's a, let's see, primary, secondary, tertiary, quaternary consumer within this food chain. So we're going to finally talk about equilibria. So this will be the last portion of our notes for today. So equilibria refers to some sort of balanced or steady state within a system. We said that it's defined in two ways, that we could have this steady state equilibrium or the static equilibrium. And in steady state, it's kind of contrary to what it's called, but in steady state there can still be a little bit of fluctuation, but if we took the average of the conditions, they would be fairly constant over a long period of time. But in static equilibrium, we're saying like everything always stays exactly the same, right? So again, in the steady state, we said there could be some fluctuation. So steady state has some fluctuation, depending on what's happening within that system. But overall, if we took an average of the conditions, they would be fairly consistent. So looking at the static equilibrium, we're saying there really is no change. If there's no change, this really is not realistic for in a natural system, because in a natural system there is generally some fluctuation as there are inputs and outputs to that system. So this static equilibrium doesn't really occur within the natural ecosystem. You would consider that steady state equilibrium with a little bit of fluctuation to be more normal within an ecosystem. So if we're looking at equilibrium is going to be stable, so that means that they always kind of return to that same balanced state no matter what happens. Okay, they bounce back. I like that this says rubber, like rubber you would consider if you had a rubber ball, you bounced on the ground and bounced back. Okay, and then there's unstable. So unstable means that it can't return to the same state. So it doesn't bounce back after something happens. So if you got into a car crash, if you got into a car wreck, your car would not bounce back after that. Okay, so it would have some permanent damage. Right, so we actually really hope that ecosystems are self-regulating. That's what we depend on. That was part of the Gaia hypothesis, that the whole Earth was kind of a self-regulating system, so it would correct any disturbances that occurred. And one of the ways that we can correct disturbances is through these feedback mechanisms. So we send some type of feedback depending on the state of equilibrium at a certain point in time. But there are two different types of feedback mechanisms. There are positive feedback mechanisms and negative feedback mechanisms. If we look at the negative feedback mechanisms, we're talking about stabilizing mechanisms. So that tries to soften the change or reduce the change within an ecosystem to produce more stability. Predator-prey relationships are considered to be negative feedback relationships, generally speaking. So if you eat too much of a certain organism, you're going to expect, so with the foxes and the rabbits, if the foxes eat too many rabbits in one season, you would anticipate then that if the fox population grew a little bit within that season, the rabbit population fell, that the next year, if there were not that many rabbits, then the foxes wouldn't have that much to eat, and then the fox population would thus decrease, allowing the rabbit population to bounce back again.